Hey guys, hello everyone. Welcome to the Science Academy, all of you. So here I am starting a new series for the GATE previous year questions. Here we are going to be discussing some questions, mostly of the organic chemistry, right? Of the all of the important topics, that is reaction mechanism, pericyclic, stereochemistry, spectroscopy, everything, right? And I'm starting from the most recent paper of the GATE, that is GATE 2022, and we are going to continue onwards 2021, 2020, 2019, and so on. And I'll try to put up upload maximum number of questions, as many as possible, right? So I just hope that you are studying and practicing. So let's start the practice over here, guys. And if you're liking this video, then please just like it and also subscribe to the channel. Also, press the bell icon, guys, because then only you will be notified by me. You will get a notification by me about each and every video that I'm uploading. All right. So yes, there are some many important and some really good questions in the GATE paper this time. See. Starting from question number 11, this is the first question that we do. The major product M formed in the following reaction is this one. Okay, so you have in the same molecule, you are having two different types of alkenes, that is a cis alkene and a E alkene. All right, so in the presence of hydrazine and oxygen copper sulfate, this is basically a reduction reaction. So in the presence of this reagent, what kind of reduction is this? It is diimide formation. Okay, whenever you are having hydrazine and there is oxygen in the presence of a transition metal, elimination of water molecules is going to take place, followed by diimide formation. Now, diimide will always reduce the less polar bonds, that is mostly used for the reduction of non-polar bonds like alkene, alkyne, right? And it is not used for the reduction of carbonyl because it is polar. Never. Carbonyl or C double bond S or C double bond N, that is imine, not used for that. For non-polar bonds specifically. But in this question, you don't have much choice. Both the bonds are C double bond C, both are non-polar. So which bond is going to be reduced first? All right. So guys, a trans bond is that also in a cyclic system. In a cyclic system, a trans bond causes steric hindrance to the molecule because it is cyclic. If you are considering an open system, a trans bond has more stability. But in this kind of a cyclic system, this trans bond is going to cause it's going to cause destabilization in the reaction, and that's why it is going to be reduced in the presence of a cis bond. Okay, so this bond is reduced, more reactive bond, that's why. So B is the correct answer for this question. Now another very important and confusing question, look over here, guys. The starting material Y in the following reaction is, so you have to give Y and three equivalents of vinyl grignard, and that is going to give you indole. Now, which kind of indole synthesis is this? Is it a name reaction? Yes, there are actually many ways of synthesis of heterocyclic compounds. You cannot remember all of them, but if you just make a list of all in your notebook and just revise one by one, then maybe you can remember a few of them, right? So this is Bartoli indole synthesis. All right, it is Bartoli indole synthesis. And since this is asked in the previous year question, I'll make a name reaction video on this also, right? Taking more examples. For now, let's discuss what is going on. So your starting material has to be some ortho substituted nitrobenzene. This could be a bromine, this could be a alkane, simple methyl substituent also, that doesn't matter. This reaction will only happen if you are having ortho substituted nitrobenzene. If you don't have ortho substituent, then plain nitrobenzene would not do this reaction, because the 3,3 sigma tropic step which is involved in this mechanism, this requires some bulky group present on the ortho position. This takes place better with bulk. Okay, so that is why some ortho substituent is required for this. Alright guys, so we are now going to see the complete mechanism of this reaction, Bartoli indole synthesis. If we start with ortho-bromonitrobenzene like this, so how is bromonitrobenzene? It is a strange reaction if you see, a little bit different, because the vinyl grignard. All right. So this is the vinyl grignard, and it is directly going to attach. See, this bond attacks over here because the nitrogen has a positive charge. Okay. So it is going to give you something like this. This is O, and oxygen is connected with this vinylic group. And now this oxygen was already O minus, no charge on nitrogen. So this is OMGBr now. Okay. Right. Now what happens is the bond is going to fall like this, and this opens up such that you are getting the nitroso now, from nitro to nitroso conversion. That is why 1 mole of Grignard is used up for this. You have a nitroso. And what happens with this magnesium bromide? It is OMGBr, and this vinylic group is over here. This is eliminated. Okay. Later on hydrolysis, this is going to give you an aldehyde. Okay. Like this. So this molecule is eliminated, 1 Grignard used up. You have 3 equivalents, right? So 2 more left. What happens next? Next, another Grignard, vinyl Grignard, is going to attack on the oxygen once again. Let's see how does it look like. If it is going to attack on the oxygen, the double bond opens up on nitrogen. So the nitrogen will have a negative charge. It is going to look like this. Nitrogen has a negative charge which is combined with magnesium like this. So this is the system that you are generating from here. When you have a bulky group on the ortho position, this reaction is going to be favored. It is a 3,3 sigma tropic rearrangement reaction like this. Which is going to give you this intermediate. All right, in this way. Okay. And now, yes, and now what happens? The negative charge on nitrogen is going to attack over here. Hence, it is going to help in the ring closing. The proton also falls up from this side onto the nitrogen, which is going to be taken away by nitrogen, guys. So you are basically going to get this kind of a molecule. You will get the cyclization. See, OH over here. Yeah, OMGBr, whatever you want to write. OMGBr. This is what you have, NH. Okay, so you have already got the cyclization. Now 1 mole of MgBr. See guys, you have used up 2 moles of methyl grignard. 1 mole of MgBr is going to now eliminate water molecule from here, because now it is going to act as a base. This proton is eliminated. Along with that, the oxygen group is also eliminated after the aqueous workup. So that is going to give you a double bond over here. All right. So hence the 3 equivalents of methyl grignard are used up, and this is your Bartoli-Indole synthesis mechanism. All right. Very, very, very important reaction. Okay. So now we move onwards to the next question, which is again a very simple question. Look at this. The major product formed in the given reaction Q is the mass spectrum uh, of Q shows which of the following peaks with the relative intensity. So when you look at this molecule, PH3P CBr4, this is phosphine, triphenyl phosphine in the presence of CBr4. You have used this combination in various places. Yes, for example, Corey-Fuchs reaction. Isn't it? You have already used this reaction, this reagent combination in Corey-Fuchs reaction. Like this, it is going to be. Phosphorus has got a negative, positive charge. This negative charge attacks over phosphorus and Br minus eliminates, which in turn is going to give you Cbr3 attached to phosphorus now, and one Br minus has eliminated. But phosphorus is still having a positive charge, right? So that Br minus, which got eliminated from here, it is going to take away a bromine and the electron density falls on this carbon. So ultimately you have PH3P double bond Cbr2. So you just generated a Wittig ylide out of this. Double bond Cbr2. So this is your Wittig ylide which you have generated, alright, through this mechanism. Now this is going to attach with this carbon and oxygen leaves with the phosphorus. So ultimately what is the molecule that you will get? You are going to get this molecule. You have Cbr2 attached, two of the bromines attached over here. Alright. Now when you are looking at the mass spectrum of this molecule, bromine has two isotopes, 79 bromine and 81 bromine if you have studied mass spectroscopy. And what is the ratio? Natural abundance is roughly 1:1. So when you are saying that 79 is to 81 bromine is 1:1, you are getting an M plus peak at, let's say, whatever mass, which is M for example. Then the M plus 2 plus peak is also just plus 2 because you are adding one isotope from here, and M plus 4 peak. You are going to get three different peaks with this intensity ratio 1:2:1. All right. So yes, guys, why is that? So why is the intensity ratio like this? Because both the bromine are 1:1, and if you are having three peaks, it is going to follow the Pascal's triangle 1:1 and 1:2:1. इसके आगे क्या होता है? 1:3:3:1, right? So if you are getting M plus 2, M plus 2, M plus 4, M plus 6 peak, that will be 1:3:3:1 following the Pascal's rule. So all of the other ones are wrong. This happens only for bromine having the 1:1 ratio. All right. Question is a very easy question here. A tripeptide on treatment with phenyl isocyanide with pH 8.0 followed by heating with dilute HCl afforded a cyclic compound M and a dipeptide. The dipeptide on treatment with pH NCS pH 8.0 followed by heating with dilute HCl afforded a cyclic compound N and an acyclic compound O. The correct sequence from N to C terminus of the dipeptide is. So basically guys, it is a very simple question. You just have to understand the language of it. So when you are breaking down, let's say a tripeptide, it's given that when you are breaking down a tripeptide with this molecule, it is just try the question by yourself and then see the answer. Okay. So it is known as Edman degradation. All right, it is Edman degradation, which is N-terminal sequencing of the amino acids of the peptide chain, right? So what is done over here is very simple, guys. You are just breaking from the N-terminus. So on the N-terminus, you are having the M acid. M is on the N-terminus, then comes O, and then comes N, and then O finally. So O is supposed to be, you are using only 2 moles of phenyl isothiocyanide, and that is why only M and N should be connected with phenyl isothiocyanide and O should be free. Okay, so let's see how it is. M is like this, N is like this, connected to isothiocyanide, and O is a free amino acid. This is exactly what we had thought. Now you just have to know about the structures of amino acid. Without knowing, you cannot do this question, right? So whenever you see, I have already discussed this, guys. Whenever you see this V, okay, whenever you see this V, which is coming from the isopropyl group, this is valine. A shortcut to remember this amino acid. So it is valine, which is present in the last and only A and C. So B and D are absolutely wrong. Okay. Let's look at M and N. So to the phenyl isothiocyanide part, see what is this molecule? It is known as thiohydantoin. Okay, the molecule which forms afterwards after the Edman degradation, it is known as phenyl thiohydantoin, and you are going to see this part is coming from pH NCS. All right, it is a shortcut. Okay, once again, NCS it is coming from, and the remaining part is coming from the amino acid. So you have COOH cut from here and cut from here. You will have NH2, CH2, and COH, which is the most simple amino acid, glycine. All right, now in between, you cut from here once again, you are going to get CH, CH2PH, which is coming from phenylalanine. You have to know the structures. So it is phenylalanine and valine. A is very simple. Tyrosine is wrong. The middle one is not tyrosine. So just know the structures of amino acid. These kind of questions are not very difficult then. Next question, very beautiful one. The major product M in the following reaction is. Once again, guys, try this by yourself and then I will definitely answer. So let's discuss this question. You can write this molecule in this manner as well because you know it is a 1,4-diene system. You have two phenyl rings and two aromatic rings connected like this. Okay. Now this is a very simple 1,4-dipymethane rearrangement, also known as Zimmermann rearrangement, right? Now, what are you supposed to do in this? First of all, the reaction requires cleavage of these two pi bonds and the formation of a cyclopropyl ring system like this. All right, this is what is going to happen first of all. And then the stability of the radicals will be involved. So I'm opening this aromatic ring and it is a para cyano compound. See, there is a cyano on the para position. So what happens, guys? I will write the same ring over here. It is the same thing. So just consider only one. Which radical is more stable? This radical is more stable because there's a benzene ring and a cyano which is electron withdrawing in nature, or a simple phenyl ring. So please understand this, that whenever you have an electron withdrawing group connected on the phenyl ring, it is going to cause a greater stability of the benzyl radical. Yes, absolutely. Do not confuse in this. A radical can be stabilized both by electron donating and electron withdrawing group. And here it is more stabilized by the cyanide as compared to simple phenyl. So it is going to cause this kind of an extended conjugation. All right, this is going to cause an extended conjugation. Radicals will always have single-headed arrow, so it is going to look like this. All right, this is what you have. So greater conjugation stability in this part, that's why it is going to be the more stable radical, this one. So always remember, the more stable radical will form the three-membered ring. And if that is the case, this bond is going to break from over here and going to give you a double bond on the less stable radical, and since it has broken down like this, you are having two aromatic groups, the cyanobenzene ones. So it is going to give you this molecule preferentially. This is the major product. You are going to get the three-membered ring over here. All right. So which product looks like this, guys? Yes, does it look like this? Two aryl groups on the same carbon forming the three-membered ring. Yes, it does. The other one, there is one phenyl, one aryl group. So you are not doing any kind of rearrangement in between these two carbons, so they are not going to change. And this forms the minor product. It is the minor product, not the major product, right? And this is absolutely wrong. No further rearrangement like this. So it is 1,4-dipymethane rearrangement. Very simple answer. Next good question. C. Major product T formed in the following reaction is. If you can just identify what's going on around in this question, it is once again super easy. So look at this molecule. You have a pyridine, 2-methoxy, 3 and 5 bromopyridine. So in the first step, you have butyl lithium minus 100 degrees centigrade. Second step, you just have a aldehyde, and this aldehyde is basically an electrophile. Now, what is happening? What is the selectivity? The question is asking you which bromine group will be removed. This one, or the methoxy is removed and then the ring is behaving as a nucleophile. Right? This is up to you guys. First try this out and then see the answer. Yes. So I would say that when you are having a bromine which is so close to the ortho methoxy, there is butyl lithium. Whenever you have butyl lithium, guys, this reaction is going to be driven by this possibility that you are doing a halogen exchange. No doubt it is not behaving as a base. You are doing a halogen exchange, but that you will do close to the oxygen because oxygen is chelating with lithium over here. So this butyl group is going to take away the bromide from over here, and your answer is going to be like this: negative and lithium positive connected over here close to the, it is not ortholithiation because we are not removing a proton, we are doing halogen exchange, but this bromine which is closer to this oxygen is going to be removed. Now you do the attack. Now you do this attack on the aldehyde. It is absolutely going to give you option number A without any doubt. Option number B is wrong. You are not removing this bromine. This bromine removal is driven by chelation with the oxygen. That's why. And you are not removing the methoxy. It's not a good leaving group, and this product cannot be explained without having an oxygen. So ortholithiation does not take place over here. Okay, no. Very simple answer. Next question, the correct reagent or reagents for the given reaction is are. Now this looks like an MSQ question, right? तो ये MSQ question है from GATE 2022. See, you have an alpha beta unsaturated carbonyl and you want to convert this to alpha beta epoxy carbonyl. Now, which is the perfect reagent for this? Yes, see all the options and do it by yourself first. Right. So you require a nucleophilic peroxide, isn't it? You know that you are going to require a nucleophilic peroxide. It is not a concerted mechanism. The bond falls back and then it is going to attack back on the oxygen. You know this. So the first step is going to be like a enolate intermediate. Like this. So this first step is going to be like an enolate intermediate. So that's what you get. In this way, epoxidation. All right. So epoxidation through H2O2 and NaOH is favored when you are having alpha beta unsaturated carbonyl because this alkene is electron deficient. Secondly, you can do the same reaction with DMDO. What is this? Dimethyl dioxirane. This oxygen is extra and it has formed by the oxidation of a ketone, right? So this oxygen can directly insert into this electron deficient double bond. Okay, and B is also correct along with this. So its answer hai A and B both. It's an MSQ question, multiple select. Next question is very beautiful, guys. See this question, you will find out some similarity in the CSIR net previous year question. The correct statement or statements about the proton NMR spectra of P and Q are. Now look at P and Q. If you have solved the previous year question of CSIR net, you will see that this same question has been asked, but based on topicity. All right, now the same question has been asked on proton NMR, right? So these two molecules, they were written like this in the CSIR net paper. They were written like this, and you had to instead of this pH, there was a COH group, carboxylic acid group, but rest of the molecule was absolutely same, right? So you see, you can draw HA and HB. You can draw, since both the methyls are above, you can draw a sigma plane of symmetry in between this molecule, cutting right from here. A sigma plane of symmetry is present in this molecule if you're writing both the HA and HB on the opposite side. Okay, so since this molecule has a sigma plane of symmetry, HA and HB, they are what? They are enantiotopic to each other since they are mirror plane reflectable. So they are enantiotopic protons. Enantiotopic protons will give you the exact same values in the proton NMR. Alright, so P shows a sharp singlet at del value 3.70 for HA and HB. This is absolutely correct. You are going to get only one single value. Alright, and guys, here only these protons are emphasized. The rest of the signals we are not concerned. Now, what happens in the next option, as you see, in the next option, you see that you cannot have a sigma plane or a C2 axis over here. The same question was asked on topicity. You can write the molecule in this way as well to check. 1 methyl below, 1 methyl above. You have this pH below now because I will be writing the HA and HB in this way. This is also correct. You don't have a sigma plane in this molecule. These two are diastereotopic protons, and when they are diastereotopic, that means they are different. So HB is going to split HA into a doublet, and HA will split HB into a doublet, and since the environment is very similar, they are going to have some values which are like very close to each other. It might look like a quartet. It is not a quartet, it's a doublet and a doublet. So in option number D, it is mentioned AB quartet centered at 3.63 ppm for HA and HB. It is not a quartet, it's two doublets for two different types of hydrogens. All right. So this is the correct option A and D for this particular answer, for this particular question. And guys, it has already been asked in CSI net just with a little change of concept based on topicity, and here it is based on proton NMR. So yeah, you see the like correlation. A previous year question asked in 2022, right? Next question is the number of peaks exhibited by T in its broadband proton decoupled C13 NMR spectrum recorded at 25 degrees in CDCl3. Now, basically, it is a very simple question. Once again, find out the symmetry elements and tell me how many magnetically different non-equivalent carbons are present. Yes, you can do so. Stop the video, do it by yourself. Now let me do it for you. Very simple. You just have a sigma plane like this. You also have a molecular plane. The molecule is planar, but doesn't matter because it is not going to give you less number of signal. This plane will. So 6 atoms on benzene. 1, 2, 3, 4, 5, 6, 7 and 8 over here. It is going to give you 8 different signals because these same 8 signals are for these the second half of the molecule as well. Very easy question. Next good question. Now these questions are of 2 marks. Previous questions were all 1 mark. MSQ, MCQ, NAT all mixed. Okay, of the organic chemistry. Now major product P obtained in the following reaction sequence is. So yes, look at this molecule guys, you might be confused. You are given NaH 2 equivalent and then second you are given methyl iodide 2 equivalent. So when you are trying to write the proper mechanism, you might be confused that maybe you are using 2 equivalents of base for 2 different carbons. And how will you write the enolate all at once? Right, but this is not happening. It is a very significant thing about the gate examination that when they want to do 2 enolate formations on, or let's say when they want back to back enolate formation, they are going to give you 2 equivalent base altogether, right? Not like CSIR examination that you have seen. So here I will be forming the first enolate. This is my first enolate which I'll form. On the second carbon, this second carbon, you can remove one more proton, but that will not give you an enolate. Rather, you are going to remove this proton such that it gives you a dianion like this. Alright, that is what you get by 2 equivalents. Now in the next step, you are providing 2 equivalents of methyl iodide. So one of the enolate is going to attack, but before the enolate attack, the negative charge has to attack. That gives you this molecule methyl, and still the enolate is there. So one more methyl iodide, like this now. On the same carbon, you are going to get this. Okay, so be careful about this. You are getting both of them on the same carbon, two methyls and one carbonyl. That is why you are given both of these things together. Second step is NH2OH and HCl. That is just forming the oxime, isn't it? So the oxime looks like this, double bond N, and the OH is going to lie on the opposite side because this side there are two bulky methyl groups, right? Next is PCl5. So now you know what you have to do. This is some Beckmann rearrangement going on. So this OH, I'm just removing the H and writing PCl4 over here. All right. What happens in Beckmann rearrangement? One of the groups migrate. Now you see that you are having two different groups. Which is more electron rich will migrate. This is more electron rich. It can migrate better as compared to this carbon. Okay. All right. So I wanted this to migrate on the nitrogen, but there is one problem with that. What is the problem? The problem is it is not going to migrate. It is so stable that it is going to form a three-membered ring like this, a three-membered, yes, with nitrogen, it is going to form a three-membered bond, which is a cyanide, and it itself is going to lose electron density because it is a tertiary and benzylic carbon. Tertiary and benzylic carbocation, 3-degree carbocation, and also it is benzylic, so it is very very stable in nature. That's why this is Beckmann fragmentation and not Beckmann rearrangement. So that is why this kind of a product, when you are getting the N substituted amide, is absolutely wrong. You are not getting the amide reduction. This is also wrong. You have to break the ring and break it from here, lose a proton. You are going to get option number A. All right, this is of utmost importance guys, that you understand first step. First step नहीं समझोगे तो ये भी wrong होगा. You might do option number D, because here in option number D, if you follow the mechanism that why we are getting D, you are getting methylation on two different carbons. That is, if you do methylation on these two different carbons, you will end up with option number D, which is wrong. All right, so be careful about this. A little thing, 2 equivalent of NaH will provide you the methylation on the same carbon. The answer is option number A. Alright guys, another very interesting question. Look at this. The major product Q in the given reaction is. Now, it is not a simple reaction, right? Look at this. You have a diene, right? And you might get this feeling from looking at the options that we need a dienophile for carrying out a Diels-Alder reaction, right? But it is not a simple diene that you are going to generate from here. In the presence of this Lewis acid, what happens is the oxygen is going to get connected to the zinc. One of the Cl minus gets eliminated. So that Cl minus is going to remove this silicon from here, which generates a charge like this. So ultimately the molecule is going to basically have this kind of a polarity. One negative charge over here and one positive. But why? What is the driving force of this reaction? The driving force, first thing, is a Lewis acid. Second thing, that this system can also be stabilized in this way. It can be considered as a allylic system like this. All right, let's say if you just do this resonance over here. All right, just one second. If you just write resonating structures in this way, all right, this can be considered as a allylic system. And when you are doing the Diels-Alder reaction or 4 plus 2 cycloaddition of a diene as well as this kind of an allylic system, let's see what is the result. It is a very beautiful reaction. It has been asked in previous examinations also. It's not very difficult. See, move the charges in such a way. See, negative charge attacks over here. It is still a concerted reaction. The pi bond attacks over here, and the electron density goes on the central carbon, so it will become negative. So ultimately, what will be the reaction? See, you are having this kind of these two methyls over here, all right? This carbon having a positive charge, the central carbon having a negative charge, okay? And this is the electron density. And sorry, you also have one bridged CH2, so this is going to be bridged like this. And this negative and positive will create a double bond. You have this example in Caruthers, it is taken directly from Caruthers, right? In the pericyclic reaction, you can check out a very beautiful reaction. You have a CH2 double bond like this. So it is a 4 plus 2 cycloaddition because the electrons are 2 only. You are actually using only 2 electrons within this cyclization from the dienophile side, just that there are 3 carbons involved. Okay, so this is your answer, option number A for this reaction. SiMe3 it cannot exist in the molecule because when it moves, then only you can generate this kind of a system. All right. Can we say it is a 1,3 dipolarophile addition? Yes, it could be because this part of the molecule is similar to that, but the reaction mechanism is concerted and it's a cycloaddition just like this. All right, all carbons are involved. Okay, so this is your correct answer, option number A. All right, guys, another interesting question. Look at this question over here. The major product P in the following reaction is. Now you have a molecule like this. One group on the benzene is a silicon, the other one is a OTF, which is a good leaving group, and the other one you have basically a beta keto ester molecule, right? You have a fluoride source. That fluoride source is mostly going to take mostly taken up for elimination of silicon like this, and if this happens, you are going to get a benzene in this way. You get a benzene, and guys, benzene usually undergoes nucleophilic substitution, yeah, addition reaction, and we can generate a nucleophile from this if we just write the enol form out of this. All right, so if we just write the enol form from this molecule, it is going to become something like this, and it attacks the benzene. So if that is the case, you will get one negative charge over here, and this carbon is connected in this way, that is you are having a ketone group and you are also having the ester group. Now the question is, which group is going to be attacked by this negative charge? It can attack over the ester also, it can attack over the ketone also, right? So we will try out both of these possibilities. Let's say it is attacking over the ester. So if it attacks over the ester, the electron density goes up like this. That is, you are going to have COO. Acha, it's not ET, it is methyl, right? So you are going to have the ester over here, and yahan pe aa jayega negative charge. So basically the negative charge will exchange a proton from the medium. You will finally have this molecule. This is one possibility. The other possibility is that the negative charge is attacking the ketone. Yes, like this. So I've written the ketone towards the negative charge. So let's say the negative charge is attacking the ketone and the electron density distributes into the ester. What does it give you, guys? Let's see. It is going to give you COMe on this side. All right. And it is going to give you the ester on the other side. It is going to take a proton from the medium. Now, which product is major? First thing, let's look in the options what is given to you. Option number A tells you that this should be the product. All right. Option number B, you don't have anything on the ortho position, this is wrong, because the negative charge which has formed, it is absolutely going to attack on the carbonyl and basically break this molecule. This has already been asked in the CSIR NET 2018 examination. Okay, please go through the PYQs. They are very similar. Now this is also wrong because we have to do this ortho substitution either with the ester or with the ketone. Now how to answer, how to understand that why this is the major product and why this is not the major product? Because a carbonyl carbon, a ketocarbonyl is more electron deficient as compared to the ester carbonyl. So that is why this attack which is going to take place on the ketone is going to be the major attack, and that is why this is going to be your major product. Okay, so a very nice question, guys. And the best part is the other confusing option is not given to you. Okay, only one correct option is given, and very important question. Yes, let's move onwards to another one. The major product P in the reaction sequence is another repeated question from CSIR net paper. Let's see what we are going to do over here. First thing, you see that it's a nitrile oxide. So the nitrile oxide is used as a 1,3 dipolar species. All right. As a 1,3 dipolar species, it is going to do a cycloaddition reaction, which is 3 plus 2 cycloaddition. So it is going to be like this. So as you can see, guys, the stereochemistry of both of these methyls will be on the same side. Let's suppose I am writing both of them above. Just suppose. Okay, I can write them below also, but I'm writing it above just like that. Okay. Now this methyl is going to be planar because it is on sp2 carbon. Second step is raninical. You have already done this in the previous year questions. I made you do in the battle of poles a lot of time. Raninical is used for breaking the heteroatom bond. So first of all, you are going to get this molecule, this methyl above, OH is on the plane of paper. So you will get NH like this. And you also have HCl and water, which is going to break the imine bond. It is going to break the imine bond and completely do the hydrolysis. So after hydrolysis, the molecule is going to look like this. It is going to give you a ketone. Now, if you are successful in writing the molecule till here, you just have to rotate a bond in this way. This is one carbonyl. You already have a methyl over here, and just a 60-degree rotation, because now you want to keep this methyl on the plane of paper with respect to this question. Okay. So just a little bit of conversion, write the methyl on the plane of paper, the OH will automatically become above. So you are doing an anti-clockwise rotation. Methyl goes down, methyl goes on the plane, and OH is going to come above like this. All right. So the answer is going to be option number A. That is what you had to do. Repeated question from CSIR net paper. Next good question. Major product P and Q in the following reaction sequence are. Now this Evans oxazolidinone has been asked various times, but just one more extra reaction is added, which is alkene metathesis. So look over here, guys. You have Evans oxazolidinone system. LDA is going to remove a proton from only one enolizable position, and then it is going to attack on the allylic or homoallylic bromide, let's say. So what do you get as an intermediate? It is so obvious. All right, it is written already. It is so obvious. These are used for chiral induction. So they are going to attack on the molecule in such a way that it attaches from below. It cannot attach from above because the isopropyl group is also above, causing steric hindrance. So C and D are absolutely wrong. Let's see option number A and B. Yes, these two look exactly the same in the first part. In the second part of the question, you are doing alkene metathesis, which is a ring closing metathesis. So just remove these two carbons and cut from here. Just remove these two carbons and add these two. This is how alkene metathesis works. It is very simple to write. All right, in this way. It is very, very simple to write down. Now, what are we going to do since we have already taken care of stereochemistry? We will just write this five-member ring over here and with a double bond because this is the new ring that you have got. Now, what is next? Next is I want to see the stereochemistry of the product ring. When you are removing this chiral auxiliary, it is Evans oxazolidinone system. When you remove this chiral auxiliary, there are many methods. If you use peracid, you will get carboxylic acid. If you are using LiBH4, you will get the alcohol. All right, so you are getting the alcohol. Let's say I'm writing LiBH4, giving you the alcohol. So this carbon is just going to be CH2OH, and now you have just got two more hydrogens connected over here. This is CH2OH. So there's no need to be confused in this. This is your product. Any bond. But we will just tilt this molecule in such a way that you get the product. How are we tilting this? We are just moving it a little bit in the clockwise direction, and you see that this hydrogen will go above the plane like that. थोड़ा सा tilt किया है. It is still above the plane, but this OH group CH2OH has now gone below. Just another way of writing the same molecule, right? This is a tetrahedral carbon. One group is above, another group is below, and two of these groups are on the plane of paper, right? So now also it is tetrahedral. These two groups are on the plane of paper and these two are above and below. That's why the answer is option number B. Just tilted 60 degrees in the clockwise direction and written the molecule like this. Same thing. All right, last question, a very good question from here. The major product M and N in the given reaction sequence are. So you look at this question, guys, it's very simple. You have sodium hydride and it is dimethyl carbonate like this. So a sodium hydride is going to pick a proton from here and it is going to basically attack over here. You can remove one methoxy and it is going to give you a molecule like this. So what have you generated basically? You have generated beta keto ester molecule. Now bromine 2 equivalent is given. So 2 equivalent bromine can add 1 over here and 1 over here, or it can add in this way also. So GATE is asking you questions with a little bit of selectivity that you can get confused in. All right, 2 equivalents. So either you are getting these two bromines over here or you are getting the bromines on the same carbon. Let's find out what do you have. And the third option is a base. So you have a base, you have a base over here like this. The base is going to remove the most acidic proton. So let's suppose if you were doing this reaction through this bromination product, because you don't have a base in option number 2, so you might think that all right, I'm removing these two protons and I'm generating a molecule like this. So if this proton is removed, you will remove the bromine over here in the presence of a methoxy base, and this is nothing but a Favorsky rearrangement reaction. All right, let's say you've got the bromide over here. All right, in that case, when the OMe attacks on the carbonyl, on this ketone, what happens is one of the bond will open up. From which side? Let's suppose on this side, because here you have the ester. Let's say it opens up on this side. You have a 5-member ring. You have one bromine over here. You have one CO2Me and another CO2Me over here and one ethyl. All right. And one more base molecule can give you elimination like this, so that you can get this as the final product. Now I want you to try out one more thing, that is, are you also getting the same product if we are taking this compound. Yes. Okay. If we are taking this compound, are you getting the same product? You will not, because, or let's say, let's try, you are having a hydrogen over here. This hydrogen is going to eliminate this bromine from this side. Okay, and let's write this with a separate pen. So you are still getting this kind of a compound. All right, there will be a carbonyl over here, which is going to be attacked by methoxy CO2Me in this way. All right. So what will happen next? Next is the methoxy is going to attack over here on this carbon. The bond opens up, and let's say the bond opens on this side. So you are still getting a similar molecule. One bromine, another CO2Me on this side, and this side you have a hydrogen. All right, yes. So you are going to get the same product when you are getting any of these brominations, right? So we will consider this one, right? So now you eliminate the H and the Br, you are going to get this product which is present in option number B. Okay, so this is what you get through Favorsky rearrangement. Let me clear up everything and let's just consider this once again. You are having the sodium hydride, remove a hydrogen from here and get the ester. So this is the dibromo product that we will consider, and we will move onwards with this. Yes, OMe. So this is one bromo. This is another bromo that you have, and we will move onwards with this one only, right? And such that it gives you this molecule, this diester. Now, after the reaction, after the M formation, you are just using dibel excess. So dibel is not going to reduce the double bond. It is used for the reduction of the esters into alcohols. That's simple. So this is your correct answer, option number B. Option number A is wrong because you are not having this double bond. You're missing this. We have one extra bromine. We can create a double bond. And here the position of double bond is wrong. You are not opening the ring on the other side. This is a minor product, wrong. And once again, guys, no sense of this. So this is basically a Favorsky rearrangement reaction which is given to you, just that you have to make the molecule. All right, guys, so many important questions from the GATE 2022 paper we have already discussed. If anything is left out, please comment. And also, if you are liking this, please also comment and share this with your friends. What else do you want me to do other than this? Obviously, the other questions of GATE are also coming up. If you want any particular question to be answered, please also comment in the comment section. I will see you all really, really soon in another video. Bye till then.